Let me record it. Right now we have 23 participants. So later on, at the end of the term, if these people come to me and ask for some favor, for sure I'll give them some favor because they tried their best to attend the class. So it might have some positive points to attending the class. But if you cannot make it, that's okay. It doesn't have any negative point. Okay. I think we can start the session. Please, everyone turn off their mics. Let me share my screen. Everyone can see my screen?
Yes, sir.
Yes.
Okay. Okay, this lecture, so as you know, we finished the first actually section of this course, which was the supervised learning, including the linear regression, multiple regression, and logistic regression. And as you know, 2 weeks ago, we started the deep learning section, the neural network. So 2 weeks ago, we had a midterm, so I just gave you a brief introduction of a neural network, a brief history of deep learning and neural network, why people decided to work on neural network again after a huge stop. And I talked a little bit about biological brain, how people actually got an idea for neural network based on biological brain. And then in this figure, you can see that how a large neural network can improve the prediction by getting a huge amount of data, because the traditional AI or machine learning algorithm, even though you increase the amount of data, the performance doesn't change after some point, right? But if you can see that the small neural network, by increasing the amount of data, has a better performance compared to traditional AI, and then after that, the medium neural network and the large neural network on the top, you can see that it has a great performance by getting a large amount of data. And the big data is actually the field that people are working on, because these days we could improve the neural network, and with a large amount of data or with a big data, we can do very great jobs. And then for introducing the neural network, I gave you an example of a top seller t-shirt, right? So the t-shirt is top seller, yes or no. It's kind of the binary classification. The output is yes or no. And then I just considered one feature, the price, right? And for example, for this one, we use the sigmoid function as an activation function. And I gave you this simple example of a single neuron, which is a unit or basic that a large neural network can be built on. So this simple neural network, which is called perceptron, it has just one single layer, with one single unit or neuron, that the main calculation is done inside this neuron. It is the core of the algorithm, right? So if you have an input, the price of the t-shirt, then some calculations, for example, here the binary classification calculation is done inside the neural network, inside this single neuron, and then it generates the output. What the output is, the probability of being a top seller. For example, it says the output would be, I don't know, 0.8. It means that there is 80% chance that the t-shirt is a top seller. This was a very simple example of classification application using a very simple neural network, which is called perceptron. Please turn off your mic. And later on, we said that this perceptron, this simple neural network, has a limited actually capability. And then people decided to use many different layers with different number of neurons. For example, here, instead of just one neuron, we have a layer like this, which contains 3 neurons or 3 cores that we can do the calculations inside each of them. For example, the input, instead of just price, now we have price, we have shipping costs, we have marketing and material, and then we can give all these 4 input to each single neuron, and then inside the neuron, some calculation is done, and then they generate some output. And the output of this layer is the input of the next layer. And then the last layer is the output layer, which shows, for example, in this application, shows the probability of being a top seller. We said that Omar Farooq, Sheng Wei. Please, when you join the meeting, turn off your mic. No one in this class likes noise. So the first layer, we called it input layer, and then we have some layers between the input layer and the output layer, the last one, which is called the hidden layer, right? So this is, for example, 2 neural network architectures. For example, the first one here on the left, you see it is made up of 1, 2, 3 layers. The first one is the input layer. Some usually people, they call it layer 0. We don't count it, but it is an input layer. And then we have hidden layers. The first one, the second one, and the last one, which is called the output layer. It generates the output. For example, if this is a top seller t-shirt application, the output will be the probability that shows a t-shirt is a top seller or not, yes or no. Or here, for example, we have another neural network architectures. So we have 4 layers, 3 hidden layer, and the last one, the output layer. And you can see that, for example, for the first layer, we have 4 neurons, 4 cores for our calculations, for the main computations. The second hidden layer has 1, 2, 3, 4, 5 neurons or cores. And then the third hidden layer has 3 neurons and 1 neuron for the output layer. Why we call it hidden layer? Because as you saw in the previous example, For example, if you have price, shipping costs, and marketing and materials, for example, the first neuron gets these inputs and generate the affordability, something else, some other features. For example, the second neuron generate awareness as a new feature. Or the last one, the third one, it generates another feature which is called, for example, perceived quality, right? It's kind of a feature scaling is done inside the hidden layers that we are not aware of them. So that's neural network job to do those feature scaling, to do those calculations internally. That's why we call them the hidden layers, because the calculations are hidden inside the neural network. So you don't need to do the feature scaling or feature engineering by manually, right? Because it is done internally by neural network. And then I gave you an example of face recognition that if you have a picture, then this picture can be converted to this two-dimensional matrix of the pixel intensity, which changes from 0 up to 255. 0 denotes the black color, and 255 denotes the white color. And then all the numbers between 0 and 255 represents the shades of gray, right? And then, for example, we use a neural network like this to recognize this image, to see this image is for who. And then I said that in the first layer, it gets these pixels, it gets this pixel intensity as an input, right? In the first layer, it detects some edges, right? Like this, and then generates some output. And the output of first layer is the input of the next layer. In the next layer, in the second layer, some parts of the face are recognized and then give the input to the last hidden layer. And here the it detects, it recognizes the face and then pass the data to the output layer. And in this layer, it generates the probability of this image to be person, for example, XYZ, right? The same thing for car classification, what kind of car it is, right? But in this session, I'm gonna talk about we're gonna deep into some details what is going on inside the neural network, and especially inside the neurons. What kind of activation actually thing is done inside each neuron. For example, let's start with this simple architecture of neural network. We have an input x vector. X vector means that this x is a list of numbers, right? Because of this arrow on the top of the x letter, it shows it is a vector, and vector is a list of numbers, right? So we give this list of number like this one here, you see? So the X was the list of number that was the pixel intensity of this picture. So let's say we give this vector X as an input to this hidden layer. So if you take a look at this, the structure of this neural network, you can see we have the layer 0, the input layer, one hidden layer, and the last layer, which is the output layer. And then we have the output. So we have an input X is given to this hidden layer with 3 neurons. But what kind of equations are or expressions are used inside each neurons? So if we zoom in this hidden layer, and you can see here, so the X was the input, a list of number like this. Let's say we have 4, right? 4 numbers, a list of 4 numbers as an X given to this hidden layer. And on each neuron or on each unit or core for our calculation, we have an equation. It runs a model. For example, the first one, it has model parameters W1 and B1. This one has W2, B2, and neuron number 3 from layer 1 has W3 and B3. And what is the activation equation for the first neuron? It is A. Activation is a terminology that people use in neuroscience, but because people, the machine learning practitioners, they used some terminologies and they got an idea of the neural network from biological brain. So they actually borrowed this activation word from neuroscience. So that's why here we call it activation. So you remember the g of z, the sigmoid function from logistic regression? So here, for example, in the first neuron, the activation is actually equal to g of z. The same thing that we had in logistic regression. And z, if you remember, was wx plus b. The same thing for the second neuron. There is another activation, actually, operation here, which is A2, which is g of z, but W2 with the different model parameters. For example, this was the first neuron. The model parameters was W1 and B1, which we used here, and then the X vector, the input here, right? And then in the second neuron, we have another activation function, which is g of z, and z in this neuron is actually expressed using these model parameters, not W1 and B1. Because we are on the second neuron, we use W2 and B2, its own model parameter, and use here. And then the same thing for the third neuron. And for example, let's say this activation function, A1 for the first neuron, calculated this number, 0.3, and this neuron calculated an output 0.7, and this one, the third one, calculated 0.2. And then we call them the activation value. 0.3, 0.7, 0.2 is a list, is a vector of three numbers, which we called it the activation values, right? And then this vector here, which we call it A vector, the activation values, a list of activation values. This vector is the output of this hidden layer here, this hidden layer, which is the input of the last or output layer. So these three numbers pass through this layer and reach out here, this layer as an input. And again, on the last layer or output layer, we have another neuron and another activation function is operating on this neuron to generate the last output, which is the result. And g of z is this equation here. You had this equation in logistic regression section, right? Which was called the logistic function or sigmoid function. So a logistic or sigmoid function was used on each single neuron in the hidden layer, right? This is how the neural network actually works, right? We have an input, we have output, and we have different hidden layers in between. And each hidden layer and each, excuse me, Give me 2 minutes. Let's go on a 2 minutes break and then I'll be back. Hello again. Sorry for that. So let's go back to the lecture. So as you saw on each neuron, we had a activation function to do some calculations, right? And here I'm going to show you some convention. For example, here you remember that we zoom in on this hidden layer and we had 3 neurons, and on each neuron we had activation function A subscript 1, A subscript 2, and A subscript 3. And A1, A2, and A3 was the activation values of the activation vector, which was the output of this hidden layer and input of the next layer. But as you can see, because this activation actually function, A subscript 1, A subscript 1 is for the first layer. You see, this is layer 1, right? This is layer 1. So all A1, A2, and A3 get a superscript, the bracket 1. You see, A subscript 1, superscript bracket 1. A2, superscript bracket 1. A3, superscript bracket 1. It means that all these 3 activation values A1, A2, and A3 are for layer 1, right? Because it is layer 1, right? The same thing for the W. So the model parameters for the first neuron was W1 and B1. So we have W1 and B1, and then with the superscript bracket 1 because they're for the first layer. The same thing for the second model parameters and the third model parameters, right? And then after getting this activation value from this hidden layer, as I mentioned, these are the input of the last layer, this one. So we got the activation layer. This is A superscript bracket 1. It means these are the activation values from layer 1. Layer 1 is here, this layer. As you can see, this is the input of this layer, layer 2, or the last or the output layer, right? So if we zoom in the last output layer here, you can see the input is the activation values from the first layer that we got here, right? And then inside this output layer, we have just one neuron with its own W and B as a model parameters. But as you can see, these model parameters has superscript of bracket 2 because they are related to layer 2. So the activation function for this neuron would be A1 because this is the first neuron, A1, and superscript bracket 2 because we are working on the layer 2 equal to G of Z. And Z here is W1 superscript 2 dot the input of the layer 2. What is the input of the layer 2? The activation vector A, right? Plus the bias model parameter B1 superscript 2, right? And then G of Z is this function here, this sigmoid function. And then it generates and it calculated, for example, this number 0.84. The output of this output layer is 0.84, which is a scalar, right? It's not a vector because just one single number. It's a scalar value. We name it A superscript bracket 2, which means it is the output of layer 2. And because layer 2 is the last layer and it is the output layer, this A is the result of this algorithm. And then, for example, if it is for the top seller t-shirt, this neural network got the X, the input, for example, like here, these numbers, for these numbers, this input are, what was this input? This input was the price, shipping cost, marketing, and materials, right? So price, shipping cost, materials was the input, right? Was the input. And then in this hidden layer, layer number 1, we had 3 activation functions on each neuron, and then got the activation values, and then gave this activation value as an input to the next layer, which is the output layer, and another activation function is run on this neuron in the output layer or layer number 2 and generate this number, 0.84. It means 84% chance that the t-shirt is a top seller. In this way, we could do the binary classification using neural network instead of logistic regression. This was a simple actually application of neural network that it can also be used instead of, for example, logistic regression. It can do the binary classification, right? And for example, even instead of the sigmoid or logistic function inside each neuron, we can use many others activation functions for different applications. But this one, we use the sigmoid function from logistic regression for each neuron to do the calculations and generate outputs, two outputs for the binary classification. Yes, it's a top seller, or no, it's not a top seller, right? For example, here it shows that we got this one from previous slide, right? 0.84. So if this number is larger than the threshold, you remember from logistic regression that 0.5 or 50% was the threshold. If this output is larger than threshold, it means the y hat or the output is equal to 1. 1 means presence of something. And presence of being a top seller. Yes, it's a top seller. If this output was smaller than 0.5, the answer was no because y hat is equal to 0, the absence of being a top seller. Any questions? Everyone can see the screen and hear my voice, right?
Yes, sir.
Okay. Thanks, Sayyid Muhammad. You're always ready to answer. Thanks. Okay. Second section, more complex neural networks. So, for example, instead of just having one hidden layer, let's take a look at this architecture of neural network. Again, we have the input X, a list of numbers, so vector X, and then we have three hidden layers. The first layer with four neurons, the second layer with five neurons, and the third layer with three neurons. And then the last one, the output layer, has just one neuron. And you can see that each hidden layer generates activation value. This is the activation A vector superscript 1 means it is a vector of activation value, which is generated by bracket 1, means layer 1. So the output of the layer 1, A superscript 1, is the input of the second layer. The second layer gets these activation values, this vector, do some calculations on each neurons, right? And then it generates another activation vector. So A vector superscript bracket 2 means the activation values which is generated by layer 2, which is the input of layer 3. And in the same way, layer 3 do some calculations on these three neurons using the activation functions and generates another activation values, another vector of activation values, which is the input of the last layer or the output layer. And the output layer, it does the last calculation using a activation function and then generates the final output. It could be a classification, it could be a regression application, right? So, for example, let's review it again. For example, from this architecture of the neural network, the let's zoom in on this layer 3 here with three neurons. And you know that this layer, the input is the activation value, which is come from layer 2, A superscript 2 here. And then on each neuron, we have activation value. For example, on this, the first neuron, we have activation function A1 superscript 3. Why superscript 3? because we are working on the third layer or layer number 3. That's why we gave a superscript 3 to this activation value, to this one and to this one. But it has different index or subscript. This is A1 because this is for the first neuron of layer 3. This is the activation value of the second neuron of layer 3. And this one is the activation value of the third neuron of layer 3. And again, we have G of Z. It could be G of Z, could be a logistic regression if you're working on a binary classification or classification applications, right? And all these three activation functions generate A1, A2, A3. And then if you string them together, string A1, A2, A3 together, you get a value of A superscript 3, which is the output of layer 3 with three values, A1, A2, and A3, right? And so for this is the general expression of what I just said. So if we have an activation function, it is something like this. This is the general expression. A subscript J superscript L, right? It is equal to, there's a lot of noise, right? Let me change my place. Uh, So, okay, you can hear me, right? And see the screen, right?
Yes, sir.
Okay. So, yes, we did the activation functions on layer 3 and got this activation vector, which contains 3 elements, A1, A2, and A3. The output of these 3 activation functions. And this was the general expression of the activation function, which is A stands for the activation value, subscript J. This J shows the jth neuron, jth, right? And then this superscript bracket L shows the number of the layer that you're working on. And then G of Z. Z is W subscript J, which shows the numbering of the neuron. And then superscript L. This shows the number of layer that you're working on times the input A, A sub A superscript L minus 1. It means this is the activation value from previous layer, the output of the previous hidden layer, which is the input of this layer, right? Plus BJ superscript L. You got it? Any questions? So we have a handwritten digit recognition here for section 3, the inference or making prediction using forward propagation. So for example, for handwritten digit recognition, as you saw in the face recognition applications, so we have the digit image of 0 and 1. We have just two numbers. And we want to get the picture of these two numbers and give this image to the neural network. And then we want neural network to recognize that image shows 0 or shows 1. So for example, we have an image of number 1 with 8 by 8 pixels, right? You remember the pixels matrix, right? For example, for that face of that lady, we had, I'm not sure, 100 by 100, right? 10,000 pixels, right? So here, for example, we have 8 by 8 matrix of the pixels. And these pixels, you see that, for example, this cell is 0, 0, 0, 0, 0, right? 0 actually represents the color black. And you remember 255 represents the color white. So if this is the image, this 8 by 8 matrix, which is a pixel intensity matrix, if you consider it as a picture, so everywhere is 255 is black, and just these cells in the middle of this matrix is 0 or white. Sorry, the 255 are white and 0 is black. 0, this one is black, this one is black, this is black, 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 up to here. So the background of this image is white, and this one in the middle is black. As you can see, it shows number 1, right? It's clear, right? It's number 1. So we want to give this image. Actually, we don't give the image to the as an input of neural network. At first, we convert the image. For example, we take a photo using our cell phone, right? And then at first, we convert that image that we took from our smartphone and change it to this 2 by 2 or two-dimensional matrix or 8 by 8 matrix with these numbers with changes from 0 up to 255. And then we get these numbers of the pixel intensity as an X, as an input, and give them to the first hidden layer. For example, here the first hidden layer has 25 neurons or 25 units, right? And then the activation function is run on each single neuron in the first layer, and each of them calculate a activation value. String them together, it generates a activation vector, which is the output of first layer and the input of the second layer with 15 units or 15 neurons. And then the same thing is done on the neurons or on the units of the layer 2, generate activation values, give it to the last or output layer, and then our result or the final output is produced. And it shows the probability of being a handwritten one, right? For example, it is 0.9. The result is 0.9. It shows 90% chance that the number is 1. This image is 1, not 0, right? So this is another actually illustration of the activation vectors, the A superscript 1, which means the output of layer 1, this layer. So if this layer has 25 neurons or 25 units, so this activation vector has 25 elements. And 25 activation functions are working together to generate 25 output, to obtain the activation vectors from layer 1, right? The same thing for the second hidden layer. So A superscript 2 is the output of layer 2. And layer 2 has 15 units or 15 neurons. And the activation function must be run on each single 15 neurons, right? So we have 15 from 1 up to 15 functions to generate the activation values, string them together, put them in this vector to generate and obtain the activation vector, which is the output of layer 2. And then this A superscript 2 is the input of the output layer to generate the final output. So as you saw, because we started here, we gave the input, the X vector to the first layer, and then we did some activation operations on each single neuron of layer 1, and then we passed the output of layer 1 to layer 2, and then again here we did some calculations, we got the result, we got the output, and the output of this layer was the input of this last layer, and then we generated the last output or result. We started from left to the right, right? If you take a look at this yellow arrow here, our calculations, this process of this neural network was started from left to right. That's why we call it the forward propagation, right? And then again, when we generated the final result, which is the output of the output layer, A superscript 3, for example, A superscript 3 is a number, right? For example, 0.7, 0.8, 0.9. If this output is larger than threshold, the answer is yes. and the y hat is 1 or the image is digit 1. If the last result, a superscript 3, is smaller than threshold 0.5, it means the y hat is 0 and the image isn't digit 1. And this way, if you give an image of a digit to neural network, it can predict that the image is digit 1 or it is not digit 1. If you have just two digits, 0 and 1. If you have more than two digits, for example, uh, how many digits we have? We have 10 digits, right? From 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We have 10 digits. If the purpose of the neural network is to recognize the 10 digits, then the output here is not just two digits, 0 or 1. It's going to be 0, 1, 2, 3, up to 9, right? And then you don't have just yes or no. You don't have just 1 and 0, right? You might have 10 outputs. The digit could be 0, it could be 1, it could be 3, up to 9. It's not the binary classification. But here, for the sake of simplification, we just use the binary classification, which has just two output, yes or no, 0 or 1, digit 1 or isn't digit 1, cat or dog, cancerous, non-cancerous. These are all binary classifications. They have only two outputs. Any questions so far from the neural network architectures, the activation functions, the process of the neural network operations? Any questions?
Hi, Professor. Excuse me. I have a question. In the neural network model, you said that for activation value, we have to use the logistic function formula.
Yes.
And but right here, we use the other formula. Can you tell me when we have to use the previous one and when we have to use this one?
Yeah,
Thank you.
yes. Thanks for the question. So, we are still here. We are using for all the examples, I use the logistic function or sigmoid function. Yes, it is based on your applications. If your you as a machine learning engineer, your job is to classify the tumor, for example. The tumor is cancerous or non-cancerous. Or they gave you an image and they tell you that use neural network and tell me if the image is cat or is not cat, right? Or an email is spam or not spam. So you need to classify the input into two classes or two categories. If you are working on such applications, you need to use logistic or sigmoid functions as an activation functions on inside the neurons of each layers, right? But if your applications is different, for example, instead of classification applications, you are trying to make a prediction, the regression, you're working on regression applications, then your logistic regression or sigmoid actually function could be changed into the linear regression model. So it depends on your applications. If it's a binary classification like here, we use the sigmoid function inside each neuron, right? But you can use different functions, different activation functions. We have many activation functions, right? So you can use whatever you want based on your applications, or you can use the combination of them, right? So later on, in the following sessions, I'm going to talk about different activation methods. But for now, for the sake of simplicity, I decided to use the logistic function or the sigmoid function for a binary classification application that we have just two output, yes or no, 0, 1. Digit 1 isn't digit 1. Cancerous, not cancerous, right? So that's why I use the logistic regression as an activation function, which is done in these cores or in these units or in these neurons of each layer. Got your answer?
Yes, thank you so much.
So in section 3, I'm gonna talk about TensorFlow implementation. So there are different frameworks for deep learning that the most three important actually framework or library that people use to run the calculations using neural networks are TensorFlow, PyTorch, and Cross. And Cross is actually is something inside the TensorFlow. So the main two framework that you can use when you're using actually neural network as your machine learning algorithm is TensorFlow and PyTorch. But here in this course, I'm gonna talk about TensorFlow, not PyTorch. So here in this section, I'm gonna show you how you can use TensorFlow as a package, a good and a strong package of deep learning that you can call it and then use and build and use the method inside the TensorFlow package to build your own architecture for neural network. So to do that, let's consider this example that coffee roasting. So when you're gonna roast a coffee bean. So there are different important factors. Two important factors in roasting coffee is temperature and the duration of roasting, right? So if you have these two features, the temperature and duration, then we are going to classify this data point that it shows a good coffee or bad coffee. For example, these red crosses represent the good coffee and the blue circle represent the bad coffee based on the temperature and the duration of roasting, right? And then we're going to do that using neural network. And this is again a binary classification application because the output will be good or bad coffee, just two output. So it is a binary classification. We can do that using logistic regression, but here, because we are learning neural network, let's do that with neural network, with a simple neural network for this binary classification. So the features X has two elements, temperature and duration, right? So for example, we can start with this example of input. Let's say X vector is 200, the temperature, 200 degrees Celsius, and the duration of roasting the coffee beans is 17 minutes. And then we give this input to the first hidden layer. And then first hidden layer actually generate the activation values, which is the input of the output layer. And then the output layer generate the activation value A superscript 2. And then this is a scalar. This is a number. And if this number or this probability is larger than 0.5, it means it's larger than the threshold. It means y hat is 1, and yes, it's a good coffee. If this number, this is scalar, which is the result of the output layer, it is smaller than the threshold, is smaller than 0.5 or 50%, it means y hat is 0, the answer is no, and we have a bad coffee. And here, this is how it can classify these data points. For example, here we have two types of data, the red crosses, good coffee, and the blue circles, the bad coffee, right? So obviously, if the temperature is too low, so the coffee beans would be undercooked, right? And it's not going to be a good coffee. So we can draw this vertical line here. So we can eliminate this area here because the temperature is too low. Or we can draw a vertical line here and actually eliminate this space because on this space, the duration is very small. The duration time is not that much, right? So too short duration to roasting the coffee. And if we draw another line here, this one here, so we can eliminate this space. This space shows that the temperature and the duration, both of them are too high. So the coffee might be overcooked. So in this way, the neural network can eliminate these three spaces and then just keep this data point inside this triangle and say that these are the good coffee. And the rest of the data points outside this triangle, they have some issue. They might be roasted in a too short time, or they might be roasted in a low temperature, or they might be roasted with very high temperature and in a very high duration time. It might be overcooked, so they're not good coffee. So let's build a model using TensorFlow. For example, let's take this simple architecture of neural network that we have an input x, the vector x. We have one hidden layer with three neurons, and then we get the activation value from this layer one, which is the input of the output layer here. And then this output layer generate an activation value, a scalar like 0.8. For example, it is like 80% probability or chance of something is present. Yes or no. But how we can build this architecture using TensorFlow in Python? So after calling the TensorFlow package,
Don't get started. Don't get started with your squeaky eye laughing.
please turn off your
What's
mics.
going on? Thank you.
Fuad
Need more
Hassan,
thoughts? No, I have one more. 5:30. I'm tired, like that's
I don't know. I think it's hard, it's hard to turn off the mic because if it was easy, you could do it in a good way, right? So maybe it's very hard to keep the mic off. So when you're talking to your girlfriend, to your wife, to your, I don't know, boyfriend, husband, kids, your parents, so everyone else, maybe it's good to hear you. I don't know. Maybe my expectation is too high to turn off the mic. So after calling the TensorFlow, so in Python, you say, hey, TensorFlow, I need to build this architecture for my neural network to do the binary classification to see if the coffee bean is a good coffee or not. So what you can do is that first you define your input. This input is a vector, right? And this vector has two elements. You remember that we consider two features for coffee roasting, temperature and duration. So the X vector, the input vector or the list is a list of two numbers, temperature, let's say 200 degrees Celsius, and the duration time, 17 minutes, right? Just a list of two numbers, temperature and duration. So here You define an array using NumPy package. So first of all, other than TensorFlow, you need to call NumPy package as well. So hey NumPy, I need an array with two elements, two numbers, 217. This is actually for the temperature. This is for the duration time. And the next line, I'm gonna build layer one. This is layer one, right? With three neurons. So layer one is equal to dense. Dense is the type of these layers. So we have different types of layers that I'm not gonna talk about the types of layers in this session, but here let's get the dense layer for this hidden layer, and the arguments inside the dense function will be the units and the activation method. So how many units or how many neurons we have in this layer? Three, right? So units equal to three, and activation method, because we use the sigmoid function because we are in binary classification application, right? So we use sigmoid as an activation method. And then we generate A1, which is the activation values generated from layer one, which is equal to layer one with input x. We define x here. After that, we're gonna build the layer number two, or the last layer, or the output layer. Layer two, this one has only one neuron. So again, dense units is equal to one, and activation method again sigmoid. And so layer two, the activation value or the output of layer two here is A2, right? And A2 is the output of layer two with which input? What is the input of this layer? The input of the last layer is A superscript 1, which is the output of the first layer. So here, as an argument of layer 2, you should put A1. A1 is the output of layer 1 and the input of layer 2. So here, as an input, you put A1. And then A1 here would be a scalar, a number like 0.8. And then you say that if this number that neural network generated is larger than 0.5 or larger than the threshold, y hat is 1. If not, y hat is 0. So as I mentioned, 0 and 1 could represent different things. 1 shows the presence of something, 0 shows the absence of something. For example, if you're working on tumor, y hat equal to 1 means the presence of cancer, and y equal to 0 means absence of cancer. If you're working on online shopping and we want to see that a t-shirt is a top seller, then y hat equal to 1 means the t-shirt is a top seller, and y hat equal to 0 means the t-shirt is not a top seller. Or in email filtration, so we are using neural network and binary classification to detect the spam, the email is a spam or not. So if we get y hat equal to 1, it means the presence of the spam. The email is a spam. If not, if y hat is 0, it means the absence of a spam. So 0 and 1 could be different things, but in different applications, but we know that 1 always shows the presence of something and 0 shows the absence of something. So let's okay, let's do another example. For example, we have this architecture of neural network with two hidden layer. This is the input. The first layer has 25 units, and then it produced the A superscript 1 as an output activation letter, which is the input of layer 2, which has 15 units. And then the layer 2 generates an activation vectors with 15 elements because it has 15 units, which is the input of the output layer. And then the output layer, there is another activation function inside this neuron and generates a activation value. And this activation value, because it is the last activation value, is the is our output, is the output of this neural network. So for building this architecture of neural network, this one, so we need to define three layers, this one, and the last one. So for the first one, we need to define our input X. Let's say it has, I don't know, it has a list of numbers like this, from NumPy, we call array. I need the array or list of numbers like this. And then I define layer one with 25 units or neurons. So I'm gonna define a dense layer with 25 neurons or units and activation method, let's say it's sigmoid. And then you can calculate A1, the activation values, which is the list of activation values, which is because it's a vector, is equal to layer one, and the argument is the input X. For the second layer, I'm gonna have the second dense layer with 15 units and with the activation method equal to sigmoid and generate the output of the vector of activation values, which is the output of layer two here, layer two, which is the input of layer three. And then here, layer two, here as an input, you shouldn't put X. You should put A1. Why? Because if you take a look at layer two here, what is its input? It is A superscript one, right? It's not X. X was the input of the first layer, but you're building the second layer here. And then its input is A superscript 1. So here, the argument of layer 2 is A1. The same thing for the last layer, dense unit 1, activation sigmoid, layer 3, and the input is the output of layer 2, A2, right? And then A3 is the last activation value, which is your which shows the chance or probability of being something, the presence of something. If it is larger than the threshold, y hat is 1. If it is less than threshold, it is 0. And another thing that is important in TensorFlow is some conventions, which is different from NumPy's because first of all, first of all, people use the NumPy for defining the arrays, right? And later on, people wanted to generate and they wanted to make a framework for deep learning, and they called it TensorFlow. And TensorFlow was actually built in Google Brain, Google Brain team. Google Brain team was the people that actually introduced the TensorFlow to the world. And so NumPy was there before that. NumPy, as you know, it is a numerical Python. It is used to define the arrays and working on the arrays, right? So it's for the numerical purposes. But the Google Brain team, they actually developed the TensorFlow, which is a framework for deep learning. And then they use Python for writing that framework, but there are some differences between the TensorFlow and the NumPy. And why these differences exist between NumPy and TensorFlow because at that time when Google Brain team was working on TensorFlow, they tried to use some different maybe conventions to make that deep learning framework more efficient. So, for example, here, let's talk a little bit about the scalar vector and matrix and arrays, what they are exactly. For example, the feature vectors. So you remember the coffee roasting example, right? We had two features, temperature, duration, and the target, which was the good coffee, yes or no, 0 or 1. 1, good coffee, 0, bad coffee, based on these two features, temperature and duration, right? So, for example, if the input actually x in neural network is actually the list of numbers, and those numbers refers to the features in a data sets. So if we have two features, so this input has two elements. So the x is an array. You can call numpy, hey numpy, I need to define an array with two elements because I have two features in these applications. The temperature 200 and the duration 17 minutes, right? And you should remember that to find the array, we use double square bracket to open this array and another double square bracket to close this array. Why? Why we use double bracket? So here, if you take a look at this two-dimensional array, a two-dimensional array in mathematics, we call it matrix. Matrix is a two-dimensional array with some rows. For example, here we have two rows and three columns or four columns, whatever columns, right? So when you are gonna define this two-dimensional array or 2 by 3 matrix, right? Two shows the rows. The first element shows the number of rows, and the second element shows the number of columns. 2 by 3 matrix, right? When we want to define this matrix using NumPy, we use NumPy dot array double square bracket 1, 2, 3, close the bracket with the square bracket, and then open another square bracket, put the second row, close the bracket, and then use another one to close the initial square bracket. So in this way, the output of this line of code in Python would be something like this, which is a 2 by 3 matrix, two rows and three columns. Or this one, this is four rows and two columns, 4 by 2 matrix. If you want to define it in NumPy, you define x equal to, hey NumPy, I need an array like this. Double square bracket, the first row, second row, third row, fourth row, and close the array with another double square bracket. So two-dimensional array or matrix could be 2 by 3 like this one, or 4 by 2 like this one, or other dimensions, or 1 by 2 or 2 by 1. This means one row and two columns, right? We call it the row vector. And this one, two row and just one column, we call it the column vector, right? But you should know that, sorry, it's not a vector because it is two-dimensional. Vector is one-dimensional. For example, take a look at here. So X is a NumPy array with 217, two elements, and then the output would be something like this, 217. It has one row and two columns. It is the dimension of this array is 1 by 2. How about if instead of this format, we define the array in this format, 200, and then come here, another line, and put 17 here. And then the output would be something like this, 2 row and 1 column, 2 by 1. It is the dimension. But if instead of double square bracket, you define an array using NumPy by just single square bracket, instead of matrix, instead of two-dimensional matrix like these ones are matrix because they're two-dimensional array. One dimension to the second dimension, the first dimension, the second dimension, right? But if we use just single square bracket, then this is not a matrix. This is not a
Hmm?
two-dimensional array. It's gonna be a vector. This is what we use in Python, for example, in logistic regression
वो लिख रहे हैं ना प्लस
as a
उसको
list of
ढूंढने की क्या
features.
दें
Omer, this is what we use in NumPy. For example, for logistic regression, we use this one, the single square bracket to define the features X. But here, this is what we use in TensorFlow, double square bracket, because we need all the vectors to be in two-dimensional, actually to be two-dimensional two-dimensional array or matrix. Why for this framework, this deep learning framework, TensorFlow, used like to use the two-dimensional array or matrix instead of this vector? This is something because of the efficiency. And at that time, when Google Brain team was working on this deep learning framework, they realized maybe if they use uh, two-dimensional arrays instead of one-dimensional, this framework would be would work better. So this is the difference between NumPy and TensorFlow and the other conventions that you should know when you're working with NumPy and framework to all your code be consistent. So as I mentioned, because we are using TensorFlow, we need the double square bracket to define our X vector as an input to the neural network. So double square bracket, 217, the temperature and time of duration for the coffee roasting, and close this array with another double square bracket, right? And then the output would be something like this, 217, but it is two-dimensional, 1 row, 2 columns, 1 by 2. This is what we need when we are working with TensorFlow. If you use one single square bracket, you cannot use it in the TensorFlow framework, right? So follow these conventions correctly. So, and here, for example, we use double square brackets for defining this input X to this neural network with the temperature and duration time. And then we define the layer, for example, layer 1 with 3 units. The activation method is sigmoid. And then the output of the first layer, A1, is layer 1 with this input X. And here, the output would be something, it has 3 numbers, right? Because we have 3 neurons. It could be a list of numbers like this, 0.2, 0.7, 0.3. And if you get this output in Python, you get something like that. TF stands for TensorFlow dot tensor. This three model shape is, or the dimension is 1 by 3, and D type, the type of the format of each element is float, which means the decimal digits, and 32, which shows the 32 bits for the memory. And this is a new format, which we call it tensor, right? And if you convert this tensor format, convert it in NumPy package, the output would be something like that. The format would be array of 0.2, 0.7, and 0.3, and the type of each element is float 32. But it doesn't show any shape because it is a one dimension. It's a vector of 3 elements, right? But here you see the shape. It is 2 dimensions, 1 by 3 matrix. This tensor actually is equivalent to 1 by 3 matrix with these elements. This is another example that, for example, layer 2, it's not another example. Here we were talking about the first layer, the same thing for the second layer or the last layer, output layer. Right here, layer 2, this one, is a dense layer with 1 unit, and the activation function is sigmoid. And the A2, the output of the output layer, is this one, layer with this input A1 that get it from the output of layer 1 here. And this is a scalar, right? But if you use TensorFlow, it shows this A superscript 2, which is shows the probability, for example, 0.8. If you use TensorFlow, it shows this format is a format of a tensor, and the shape is 1 by 1. It is just one number, but the dimension is two, is 1 by 1. It shows two-dimensional array, even for this single scalar. But if you change it to NumPy, this tensor or this two-dimensional matrix to NumPy, it shows array. It's an array. It's a one-dimensional array, not two-dimensional. There's a difference between the NumPy and TensorFlow. There are some differences that you should be aware of them. Building a neural network. So what you saw earlier, we're gonna modify it a little bit, organize the code a little bit. For example, this is what I just mentioned. If you have this architecture, at first I define the input X. For example, for coffee roasting, the first element of the input X is the temperature. The second one is the duration time. And then for the first layer, I define it like dense, unit 3, activation is equal to sigmoid. And for obtaining the A1, the output activation values of layer 1, I write this line of code, layer 1 with input X, and then I can calculate A1. And then for building layer 2, I use dense method, unit 1, activation method sigmoid, and use layer 2 with the input which is generated from layer 1, which is A1, which is the input of this layer, right? But we can modify and organize this code a little bit. For example, here we can write the layers first instead of write this X, the input. So layer 1, this layer, is dense layer with 3 units and the sigmoid activation function. Layer 2 is a dense layer with 1 unit and sigmoid activation. And then use a sequential method to build our neural network model. Sequential method actually a sequential method actually string these two layers together, right? And then get a stack of two layers. And then we can define the x using a NumPy array, something like this. It's a 4x2 matrix, right? Remember, we use double square bracket to generate a two-dimensional array because we are using TensorFlow framework. And then let's say we have this data table like this. The first column is for temperature, the second column, the second feature is for duration time, and the last one is the target, good coffee or bad coffee. We define X using these two columns here, 4x2 matrix. This is 4x2 matrix. And the Y, the target, is just this one-dimensional array, 1, 0, 1, 0 here. And then in the next step, here, we compile our model that we built here, and then fit the model on the data set, X, Y, that we just defined here. And X, Y shows this data table. We fit our model on this data table. And then in the last stage, we can predict the new set of data using our model. This is how the neural network works using TensorFlow. Or instead of this way, you can build your model in this way. Model equal to sequential of the first layer and second layer, right? With 3 units and 1 units. Then define your X, your Y, and compile the model and fit the model on the X and Y, this data set. And then you can predict a new set of data. For example, here is another architecture of neural network. We have 3 layers. So first of all, you can define your first layer using dense method, the second layer, the third layer, and then use the sequential method to stack them together, right? Layer 1, layer 2, and layer 3. And then compile the model, define X and Y, your data set, fit the model, and predict a new set of data using your model. So we have 2 more pages. Let me go through it quickly and finish this lecture. So instead of just going on a break for 10 minutes, but we can finish it together. We have only 2 more slides. So in this section, neural network implementation in Python. So in this section, I'm going to tell you a little bit about how TensorFlow works. So later on, maybe some of you are very curious, some of you really like this field and want to introduce a new deep learning framework to the world besides PyTorch and TensorFlow. So you need to know what is going on a little bit at least, that what's going on in TensorFlow, how it works, how people use Python to write the TensorFlow framework. So here, I'm going to show you that this is a forward propagation because we start from left and then we reach out to the last stage on the right-hand side for the coffee roasting model, for example. So first of all, you know that we have an input, right? We define input X, using a NumPy array, and then this array has two elements, the temperature of the roasting process and the duration time of the roasting process. This is our input X. And then the first layer, as I mentioned, we have uh, three neurons. And you remember that each neurons has its own function, right? Activation function. So for example, the first neuron here is G of Z, and Z is W1 times X plus P1, right? And then you can define your W1, right? It's a NumPy array. Let's say it is 1 and 2, right? And then why it has two elements, W1? Because your X has two elements. What is X? X is the list of numbers or list of features. You know what was the feature, right? You know what the feature was? For example, for pricing of the house, the example of pricing the house. The size of the house, the number of bedroom, the location, the age of the house, all of them were feature. And then the target was the price of the house. This X is list of features. Because here we have two features, we have two numbers, the first one for the temperature, the second one for the duration time. So it means we have two features. When we have two features, we need to define two weights for two features, right? So that's why W1 for the first neuron has two elements. Let's say it is 1 and 2. These are the two weights for these two features. And then bias parameter B1, 1. B11 means the bias parameter, model parameter of neuron 1 and layer 1. And then Z1 will be WX plus B, right? This one in the parentheses. And A1 is the output of the sigmoid function of this Z that I just defined. So this is A1 from this first neuron. The same thing is done in the second neuron, and it generates A12. It means the activation value from the first layer and second neuron. And then the same thing in the third neuron, A13. It means the activation value from the first layer and neuron number 3 or unit number 3, this one. And in this way, you have A11, the output, the activation value of the first neuron of first layer. You have A12, the activation value of the second neuron and first layer. And A13, the activation value of the third neuron in the first layer. And then string them together, you get this array, which is A1 here. This A1 is a list of numbers or is the array of this A11, A12, and A13. Now A1 here is the input of the output layer, right? And here in the output layer, we have just one neuron. We do the same thing that we did for these three neuron. We do the same thing on this last neuron. And we get A21 using the sigmoid function, which is the output or which is the activation value of the layer number 2 and neuron number 1. Layer number 2, this layer, and neuron number 1 because it has just one neuron. And this is A2, the output of this neural network. Right? It is how the neural network works. And people introduced and they built a framework called TensorFlow and then put all this process together in a very nice function and format that later on, when you are going to write the code, you don't need write all these things in your code because all this process are done previously in the TensorFlow, and then you can just call the TensorFlow and use those functions and build your own neural network architecture. And then what people actually did in TensorFlow, so this is something like this. So in TensorFlow, they define the function like dense. So you remember that you easily use dense function, right? Dense function to define your layers. For example, here we have 3 layers. You use dense method 3 times to define your layers. But how this dense function is built or is written in Python, this is what the Google Brain team did in TensorFlow. They defined the dense function before, and now these days you can easily use this dense method to generate and build the layers of your neural network. But how this dense function is written originally is something like this. They define the dense function with this argument, the input, the W and B, the parameters, right? And then they wrote this code here. I'm not gonna go through it. And then the sequential function. You remember the sequential function here? You easily just call the TensorFlow and use this sequential function to string all these layers together to give you a complete model of neural network. But how this sequential function is written, how it is working, the Google Brain team, yes, they built these methods, the dense and sequential function. These days you can easily use it. But how it works, this is something like this in these 2 slides. Slides number 17 that I just mentioned about the process, and then slide number 18. They define the dense function and sequential function like this. You don't need to go into the details, but at least if you're curious, it can give you actually give you some general idea how it works, and then you can study and learn about it by yourself, right? So this was actually about the neural network. The first lecture, we have, I think, 3 or 4 lectures for neural network or deep learning. This was the first lecture of neural network. I hope at least you learned a little bit about neural network and the process of its learning and how it can make a prediction. Do you have any questions or concerns? I think that you don't have any questions, right? Everything is good?
Yes, sir.
Okay. Okay, good.
Yes, sir.
Okay. So again, if you have any questions, if you have any concerns, you can reach me out, send me an email. I try my best to reply your email and anytime, at any time, even during weekend. And then if you have any special concerns or questions, we can make a Zoom meeting and talk to each other, or we can talk on Mondays when I'm at university. So, okay, let's call it a session and have a great day.
Thank you, sir. You too.
Thank you, sir.
No
Thank you, sir.
problem.